Hi everybody, welcome to this class on advanced algorithms for optimization. We will start with a very well-known topic, which is dynamic programming. It's a technique that you can apply for solving some discrete optimization problem. And we will start first with a brute force approach for solving that problem using a recursive procedure. Just to explain the high-level intuition of this knapsack problem, the motivation is the following. A virus has contaminated your laptop and everything will be erased in a few seconds. And the only thing that you have to save as much files as possible is a memory stick. You can also evaluate how much you would like to save each item of your laptop. For instance, you have a bunch of pictures, you have a bunch of zip files, you like the lib files with a value of 10, for instance, and each of them also has a memory value. For instance, this one would require 3 GB. So for instance, you cannot put the 8 GB file and the 3 GB file inside this memory stick because it only has a capacity of 10. And the goal here is to maximize the amount of value that you will be able to save given the capacity constraint of the memory stick. Let's formalize this problem in a mathematical form. We will define the set of items that you might consider to save on the memory stick. And for each of them, you have to decide, these are the decision variables, you have to decide a binary decision. 0 is you don't save it, and if you put this variable to 1, xi, it means that you would like to put the item I on the memory stick. Vi is how much you love. You would like to save this item, so this is the value, and of course the value I will be taken into account in the objective function if you would save this corresponding item. Of course, you have here the capacity constraint that are also using the weight, so the amount of memory that it would require to save this item, and this is the capacity, so the memory stick capacity. Okay, so the goal here is to select as much value as possible given the capacity constraint that you have here. This problem is known as an NP-complete problem, and there is an easy reduction. Okay, so you do the reduction in that direction. There is an easy reduction from the subset sum problem. Okay, why? Because this problem is not harder. Is at least as hard as the subset sum problem. Because if this problem was easy, you could easily solve the subset sum problem as well. You just have to replace, here this by k, the k from the subset sum problem. The vi that you will use is ci, and you would use ci here as well. Okay, and then if you can find a solution, you've got a solution for the subset sum problem, which of course means that this problem is at least as hard as the subset sum problem, so it's also an NP-complete problem. One possible approach for solving that problem is the brute force approach. So you will try every possible combinations for the binary decisions. If you have n items that you would like to consider, it means 2 to the power of n is the number of solutions that you need to consider. And so this is an exponential function, okay? And so this is, for instance, the function 2 to the power of n, and size n is here, okay? Already for 50 items, this would require a huge amount of time to solve this problem. And the goal here of this lecture is to explain to you not how to avoid the exponential behavior, but how to shift it a little bit to the left so that we can consider a little bit larger values, larger instance size for that problem. So the brute force exploration, if you want to enumerate all the solutions, you can view this enumeration as a search tree, okay? So this is a small instance here. You've got the index here of each of the items. So this is an instance with 5 items, indexed from 0 to 4. And for each of them, I've got the value and I've got the weight that it will require. So the amount of memory that you need to put inside the memory stick. And this is how much you would love to save this item inside the memory stick. Okay. And you will enumerate a search tree like this, considering binary decisions. So a plain line like this means that you would save the corresponding item. So item 0, you save it. And a dashed line means that you don't save it, you don't take it. Okay? And so if I go completely there to the left, it means that I'm saving everything. And if I go completely to the right, it means that I'm not saving anything here. Okay, and as you can see, I've got 32 combinations here already. For 5 items, I've got 32 combinations, so 2 to the power of 5. Initially, my capacity is 11, and so this is what I will represent here, is the amount of capacity left in my knapsack. If you take this item, so if you take the first item, your capacity left, because it has a weight of 2, your capacity left is now 9, okay? And if you don't take it, the capacity left is still 11, right? Then you consider the second item, this item, item 1. If you take it, you see that it requires memory of 3, so the capacity left here would be 6, and if you don't take it, it's still 9. If you take it here, 11 minus 3, it's 8, and if you don't take it, it's 11. You continue like that, and at the end, you have explored all the possible combinations. Let's formalize how we would implement this brute force approach, and we will consider the problem with a given prefix of items that you have already considered. We will go up to the item j here, okay? From the item 1 up to item j. And we will denote the optimal objective function as okj, okay? This is the optimal solution for a problem with capacity k, considering the items from 1 to j, okay? And so okj is really this problem. You want to maximize only over the items from 1 to j, and the capacity is k. And these are the two parameters here of my objective functions, okay? And of course, what I would like to discover is the optimal solution for the initial instance, which is OCN, okay? So the capacity is C, and N, this is the number of items for the whole problem. I can write recursive equations for solving that problem, okay? And the recursive equations will basically consider two possible choices for a given item j. Either you take it and you go to the right, or you don't take it and you go to the left, okay? Exactly as we did before. If you remember, you take it and you don't take it, okay? It means that xi is equal to 1, and here it means that xi is equal to 0. Okay, and this is what I'm considering here in my recursive equations. So the optimal solution of okj means that either I don't take it or I take it. If you don't take it, it's here. Don't take it. Okay, it means that you don't take it, you simply recurse on g minus 1. But the capacity remains unchanged. You still have the capacity of k. The other possibility is that you will take it, okay? It is if you go in that path, okay? If you take it, okay, this is the blue part here. If you take it, the amount of value that you take is at least the amount of the item j, because you select it. So the objective function will be at least increased by v of j, plus the optimal solution with items j until j from 1 until j minus 1, but you should also decrease the capacity here, okay? So if you start with a capacity k, the capacity that is left here in your state is k minus wi, okay? And this is what I'm putting here in my recursive equation, okay? And of course, you have to take the maximum of the two possibilities. You don't know what will be the value on the left part and what will be the value on the right part, but the one that you want to take is the maximum of the two. You will take the maximum of the two, which is represented here, okay? Yeah, sorry, this should not be there. And you also have the base case, because when you have a recursive equation like this, you also need to stop it at some point. And the base case, the time at which you need to stop the equation is whenever j is equal to 0. Okay, it means that you don't have any item to select. Okay, you cannot select any item, and so by definition, the total objective function for a problem with 0 items is 0, and you will do that for all the k here. In the next video, we will translate this as a Java source code.